Good evening, and welcome to the first lecture of the 2020 UTU season. Tonight, we will hear from Dr. Darryl Butt, Dean of the College of Mines and Earth Sciences. I am Brooke Abel, coordinator of the UTU lecture series. Before we get started, I have a few housekeeping items. Thank you for your continued patience and understanding as we transitioned the UTU series to a virtual format. As you may know, we are partnering with the university's Alumni Association to provide these lectures to a broader audience. I offer a sincere welcome to all University of Utah alumni joining us tonight. If you are a UTU member and haven't submitted a donation or refund request yet for your 2020 membership fees, please click on the link provided in the YouTube chat. If you have any questions for Dean Butt, please email clubs@alumni.utah.edu or comment in the YouTube chat throughout his presentation. We will address your questions during the Q&A portion of the event. It is now my pleasure to introduce Dean Darryl Butt. Dr. Butt has been the Dean of the College of Mines and Earth Sciences since 2016. He is a professor of material science and engineering and also the director of the Energy Frontier Research Center at the U. Prior to joining the University of Utah, Dean Butt was a distinguished professor of material science and engineering at Boise State University. He was with BSU for 11 years, serving as department chair between 2008 and 2013. And as an associate director of the Center for Advanced Energy Studies from 2007 to 2016. He has held various academic, research, and leadership positions with Ceramatech Inc., AP Green Industries, the University of Florida, and the Los Alamos National Laboratory. He has authored or co-authored approximately 240 peer-reviewed publications and 10 patents. Dean Butt, thank you for joining us.
Thank you, Brooke, and thanks also to Amy, Nellie, and Emily for helping to organize this, and thanks to TJ too, our development director. And thanks to all of you for joining us this evening. I hope you're all comfortable. I can't see you. I wish I could, and I wish we could sort of hang out together, but these are strange times, and we'll adapt and change. So I did change the title of the presentation slightly, and I apologize for that. It's for two reasons. One, I honestly forgot what the original title of the talk was, and two, I thought I'd try to make it a little bit lighter, a little more fun, and I'm kind of shifting the focus of the presentation from being a little bit heavy on science and technology to being a little more focused on sort of the cultural aspects of what I do. Again, I'm the Dean of the College of Mines and Earth Sciences, which is a really fantastic college at the University of Utah, and we'd love to have you come visit when things get normal, and thank you very much for joining this presentation. So the talk I'm going to give today has kind of two underlying themes, or two concepts that I want to make recurring themes. And the first one is the idea of transdisciplinarity. And when I use that term, I don't mean multidisciplinary, I don't mean interdisciplinary. What I mean by that is knocking down the barriers of disciplines, in a sense. In academics, we have silos. We operate as colleges and departments. We often try to compartmentalize or categorize people in terms of their degree, in terms of, and make that their identity, in a sense. And so when I use the term transdisciplinary, what I mean is when I bring students together in a class, or I bring students together to try to solve a problem, we try to forget about their discipline, and we ignore the discipline boundaries. And what that allows you to do is, in a sense, solve bigger, more complicated, messier problems. And the second theme that I'm going to kind of try to touch on today is what I call unpredictable outcomes. And what I mean by that is trying to arrive at better decisions by overcoming your bias. The whole process of scientific inquiry is often based on having a hypothesis and then trying to prove or disprove that hypothesis. And the very fact that you begin with a hypothesis means that you have a preconception of where your research or your investigation is going to go. And if you're biased, that often leads to taking paths that are perhaps unwise or unfruitful. And if you can put people together in diverse groups or make use of a diverse set of tools in order to solve problems, you identify more solutions and hopefully arrive at better decisions. So those are two underlying themes. I'm going to kind of make use of elements of a series of courses that I developed at my previous institution. And we called these vertically integrated projects. And this is a term that's used nationally now. We refer to them as VIP courses or the VIP concept. And I taught the first VIP course at my previous institution. It was called The Science of Art. And the long title of the course, the working title, was actually Preservation and Reverse Engineering of Cultural Heritage. And there were several different sections. A student that enrolled in the course was expected to take at least 2 semesters. The first time I taught the course, the theme was the science, history, and psychology of the color of art. It was, we had a textbook for the course, but it was essentially a flipped classroom where I would do a little bit of lecturing, and then we would just brainstorm together, and students would go off and carry out research in the laboratory or in the library or wherever. And there's a really cool book that we use called Just Color by Victoria Finley. So this is kind of where the gist of this presentation comes from, my experience in teaching this course and in teaching these students. And it was a really pretty novel, innovative course at the time. And I'll elaborate on that a little bit more here in a minute. So as I said, it was project oriented. And so we had a variety of projects, and I won't go through all of these, but these are just some pictures that illustrate the things we worked on. And the whole idea was to develop a problem or a project that was so much fun that the students just couldn't help themselves but work hard at it. And I used to be a soccer coach. I coached for around 24 years. And one of the things I learned as a coach is that if you want your players to be in great shape, super fit, if you want them to have the skills that are necessary to be great soccer players, you don't make them run laps, you don't make them run sprints, you don't over-explain the skills that you're trying to develop. What you do is you set up games that are so much fun that the players don't realize that they're working hard and developing physically and mentally, and the skills just come naturally. And so the idea of this class is kind of based on my experience as a soccer coach, in that what I would do is I would identify a problem that was so incredibly fun that the students just couldn't stop working at it. And today I'm going to talk a little bit about this guy over here on the right. Let me see if I can get a laser pointer here to work. There we go. Hopefully you can see my little laser pointer. So we're going to talk a little bit later on in the presentation about this mummy portrait here. And I'll come back to that in a moment. So bear with me. The organizers of this asked me to say a little bit of background on this presentation. And I'll just tell you, the first time I gave this talk was actually at a conference in India. I was asked to give an invited talk on diversity in education, which is something I've been interested in many years. And I thought I was just going to give a presentation in a sort of an auditorium. It would be a PowerPoint, and I would just talk about some of my experiences. And it turns out that it didn't work out that way. And when I got to the facility, it was gigantic. It was, and I ended up giving a presentation sandwiched between 2 gigantic gold statues. This is one of the statues. This is the goddess of education, and you can't see it in the picture, but on the other side was a giant gold statue of Gandhi. And I wasn't able to use a PowerPoint, which kind of threw me off a little bit. Instead, they stuck me out on a podium. This isn't me. This is a speaker that came after me. But they stuck us out on this podium, kind of like being on the plank of a ship, and with no handicap, or no crutches, I should say. to protect me. And in front of me was a camera. I was speaking to about 5,000 teachers at the time out in front of me under this gigantic open tent. And at the same time, they were projecting my image to about 20 million teachers in India. So it was kind of, it threw me off a little, kind of intimidating, to put it mildly. But to make it even more intimidating, you'll notice down in the lower corner, there's a newspaper down here, and that's a picture of the Dalai Lama. And they were telling us that the Dalai Lama was going to show up at some point. And I thought, yeah, right, he's going to show up. Well, it turns out the Dalai Lama did show up, and this is him. This is a picture of the Dalai Lama on stage, and he's being projected on a big screen behind him. And he gave this incredible presentation. Everybody was laughing. He was running around pretending that he was a teacher, hitting people with a stick. And you can see this is a friend of mine with his hand on his face. He was kind of embarrassed. So I followed the Dalai Lama. The first time I gave this presentation was kind of like following a stand-up comedian, and presented it to about 20 million people in India. So that's the story of this presentation. So, and after I followed the Dalai Lama, which was pretty intimidating, I started my presentation like this. So I said, butterflies see the color purple really well. And then I allowed for a long moment of silence, and everybody stared at me kind of funny. And then I said, butterflies see the color purple really well. They see color from somewhere between yellow in the visible spectrum for us, well into the ultraviolet region. So if you take a butterfly that, let's say, is white, and you carry it gently into a closet and shine an ultraviolet light on it, what you'll discover is that that white butterfly is not in fact just white. It has an exotic pattern on it. So what to us might look rather boring, to a butterfly might look rather interesting, exotic, and even beautiful. So butterflies see the world different than us, and that's because of their visible spectrum. If we had a flower, for example, that was yellow, a butterfly might see it as sort of a green and purple flower. In other words, a butterfly might see more information in something than we can because of its ability to see in a different wavelength than we do. And that's what I do as a material scientist. That's what we do as scientists. In a sense, we shine light on things. And this is a table of the fundamental entities or particles and waves, which I like to refer to as sensible energy. In other words, all of these particles, all of these forms of waves of energy are sensible and therefore, in a sense, visible and understandable to us. My two favorite particles or waves are the electron and photon. So I spent a good bit of my life using those to analyze materials. And when I say we shine light on things, I mean that in both the literal sense and the figurative sense. So we shine light on things literally in order to resolve chemical information or structural information, but we can also shine light on things in more of a figurative sense or a metaphorical sense by bringing people with different ideas and from different disciplines to solve a problem. And we have big problems in the world right now. And this is a skill that we really need to develop in our students. The skill to work with one another, the skill to overcome your own bias, the skill to see things in a broader wavelength, if you will, broader span of wavelengths. My favorite tool perhaps is the synchrotron. And this is like a gigantic flashlight that shines light on things. The way a synchrotron works is essentially you have a source that produces electrons, and you accelerate these electrons around a circle. Basically, as you accelerate them and run them through a bunch of magnets, you bend them, and they get going faster and faster. And when an electron bends, it loses a bit of its energy. And that energy is translated into what's called synchrotron radiation, or what we call bright X-rays. And these bright X-rays can be channeled to basically a station of some sort where we can analyze a material, and there's a whole bunch of detectors. So if you go to a synchrotron facility, you'll notice these stations all around it, and there'll be researchers in this station. And what they're doing is they're making use of the bright X-rays that these electrons create as they're bent. A couple other tools that I love to use are the transmission electron microscope, or TEM, and the what's called the secondary ion mass spectrometer. And the TEM is very similar to a synchrotron in that it uses electrons, but instead of having electrons travel in a circle, they travel in a straight line, and they are transmitted either through a material or they bounce off a material. And in a TEM, we can actually image atoms. We can identify the position of atoms. We can identify the chemical structure. We can identify the crystal structure. A secondary ion mass spectrometer operates a little bit differently. What we do is instead of sending a beam of electrons at a material, we send a beam of ions at a material, and these very high energy ions sputter other ions off the surface, and then we can analyze those ions and learn things about the chemistry of a material. We can also date materials using instruments like this, and very powerful, very expensive tool, obviously. So I'm going to talk a little bit about some of the work we've done with tools like this in a little bit. But first, I just want to say a little bit about transdisciplinarity. And this is a familiar face. I'm guessing many of you have seen this drawing before in chemistry books or physics books. And there's no question this is a drawing by Leonardo da Vinci. It was found in his notes. It's in his style. It was drawn with a red pastel, which he's known to have manufactured himself. Da Vinci was an incredible human being. He was uninhibited by discipline. He was an artist, a painter, a colorist, a botanist, probably a pathologist. He really was interested in military science, so he's probably a military scientist and a mechanical scientist. He was a very humble person too. At times, he was willing to organize weddings. He was a set designer, event planner, a writer, and a musician. On a personal side, Leonardo was also the son of a slave. His mother was probably a 15-year-old slave. His father was a notary. Because he was an illegitimate child, he wasn't allowed to attend universities. And that may be why Da Vinci was such a transdisciplinary person. He wasn't compartmentalized. He wasn't bound by disciplines. He was not afraid of failure. People today are afraid of failure. Da Vinci was not. He was believed to be very handsome. He was left-handed, which was frowned upon in those days. He had an interesting habit of writing in reverse. I remember our son actually used to write his name in a perfect mirror image backwards, and it kind of freaked me out, to be honest, when I first saw him do this. And he did it for quite a while, and then it sort of disappeared. That never disappeared for Leonardo. He wrote in reverse his entire life. So bottom line is, Leonardo was a savant. He was a genius. This is our image of a Renaissance man. This is our image of a genius. This, by the way, is what Da Vinci's picture looks like now. It's degrading severely. After World War II and during World War II, it was exposed to the elements. It's foxing, it's becoming embrittled, and the chalk is falling off, his signatures is gone. One of the things that's happened in recent years is that we've also dated this image to sometime in the 1490s. And I don't know if you noticed in the previous image, I showed his birth date as being 1452. So I'm having a little problem with this image. So this image of someone who's supposed to be very handsome was painted apparently or drawn as a self-portrait by someone who would have been about 40 years old at the time. And I don't know about you, but this doesn't look like the image of a 40-year-old handsome man. So I think it's probably questionable that this is a picture of Leonardo da Vinci. We all believe it is, many people do anyway, but it probably is someone that he found on the street or a colleague or a friend. But this is our image of a genius. This is This is just like Einstein. We have this image of what a smart person looks like, what a brilliant person looks like. But in fact, this probably isn't what Da Vinci looked like at all. Just food for thought. So the transdisciplinary course concept that I use is kind of illustrated best by this diagram. And when I first taught this course, I had the luxury of handpicking students, which sounds like kind of a biased thing to do, but I limited the size of the course to 12 because I only had a certain amount of resources to dedicate to the course. And students had to apply and they had to be interviewed. And what I was able to do is design a course that was very diverse, or design a group of students that was very diverse. So I had gender equity. I had students that were sophomores, juniors, seniors, and graduate students. I also had a wide distribution of disciplines in the course. And so I had students from psychology, sociology, material science, philosophy, art history, visual arts, chemistry, public policy, art conservation, and social work, all trying to solve a problem. And, you know, it seems like kind of a strange mix of people, but when you put a bunch of people together like this, amazing things happen. And this isn't something that was kind of new to me, just kind of a personal example of things I've done in the past. I used to work at Los Alamos National Laboratory, as you heard earlier, and when I was there, my title was Lead Project Leader for Nuclear Weapons Dismantlement and Fissile Materials Transparency. And I had a second position at the same time, was Project Leader for the START Tree 3D. And when you put those two things together, they don't fit on your business card. So my official title was Lead Project Leader for WD and FMT. And my job was to bring together a large, really complex group of brilliant people and try to understand how to dismantle nuclear weapons in America and Russia at the same time safely. It was an incredible experience. And, you know, thinking about it retrospectively, I actually really at the time didn't even know what anybody's discipline was, and I didn't really care. And we just brought together this group of incredible people that were brilliant to try to solve a really challenging, complicated problem. So that's kind of the model that I used in the class, believe it or not. But instead of trying to dissect or dismantle a nuclear weapon, we would, for example, try to dissect or dismantle a painting or a piece of art or a piece of history. And in order to make this group of students more effective, I provided a number of other external resources. So this wasn't a normal class. So in addition to the normal class time, they also interacted with my research group. So they interacted with the students and postdocs in my group. They had access to my lab. They also had access to a couple of museums. They had a mentor at the Walters Museum and the Smithsonian. They had a couple of mentors actually at our state historical archives. There was a librarian that was involved. We had a faculty member from art history who also helped me teach the class at times, someone from the art department, and we had two faculty in the English department, all serving as mentors to this group. And the whole idea is that we flipped the classroom, and the class was also very dynamic. In other words, we had a syllabus, but the syllabus could change during the semester, and the students had control over the direction of the class. So kind of a really unusual format for a class, but it was really designed in order to solve significant problems and real problems. So in order to kind of make the class work together well, I spent a lot of time trying to teach them about bias and how to overcome bias. And this is just kind of a nice little example that I used during the semester. Many of you have probably seen this. It's a classic example of how to understand your own bias. And I'm going to do a little experiment here in a second, or a little illustration. And if you don't buy it or you don't believe it, pick up a copy of the book Blind Spot. It's a really fantastic book. And this example is in chapter 1 of that book. So there's two tables here. You can see they're obviously different. The table on the left, I've looked at this many times. To me, looks like it's pretty narrow compared to this one that's a little bit wider. This one's a little bit longer, this one's a little bit shorter. But if I take the table on the right and I rotate it and I superimpose it on the table on the left, what you discover is that they're actually exactly the same dimensions. And I'm going to reverse that. And no matter how long you stare at this image, you will never convince yourself that the dimensions of the table on the right are the same as the dimensions on the table on the left. And this is, an issue with human beings. When we take a two-dimensional object and we try to convert it into a three-dimensional object, we immediately convert the dimensions accordingly to satisfy our implicit bias. And this is a problem not just when we're trying to analyze a two-dimensional object. It's a problem for us when we're trying to understand scientific results, trying to interpret our research. It's a problem when we interact with human beings. We all have a preconception. For example, we have a preconception of what a genius looks like, what a smart person looks like. So this is just a small example, but if you do this over and over in the classroom, if you have lots of examples in the classroom that help students understand their bias, and you try to help them listen to one another, amazing things happen. And they start to understand and make connections between their own implicit bias and the value of diversity. So to kind of convert that idea into, a way of operating scientifically, I always reiterate this simple statement over and over during the semester. And I do this in every class that I teach. So I always, and I just do it in the context of the class that I teach. So this statement, for example, can be filled in with different types of concepts. You can say proof of fill in the blank, proof of provenance, proof of provenience, proof of a theory, proof of a hypothesis, proof of a mechanism, proof of a scientific concept. Is less like a mathematical proof than it is like a proof in a court of law. So in other words, when you're trying to understand a scientific concept, when you're trying to prove something or understand something, it takes lots of pieces of evidence. That evidence might be in the form of different diagnostic tools, or it might come in the form of ideas from different kinds of people, from different kinds of backgrounds and different kinds of disciplines. And so in order to understand something in science, it's of great value to look at it from many different perspectives, both analytically and socially. So the title of the class, as you'll recall, had the word reverse engineering in it. So the whole idea of the class, and this is what I do in my group too, is we often try to reverse engineer something. In this case, we're trying to reverse engineer, for example, a piece of art. And reverse engineering can be described in different ways, but it basically is the discovery through analysis of structure, function, purpose, operation, provenance, and provenience. And these terms mean different things to different people. So for example, structure means something different to an artist versus a historian versus an architect versus a philosopher. And but nonetheless, everybody can reverse engineer something from their own perspective and bring those ideas together. So if, for example, I ask you to reverse engineer this lovely painting, and I say, I want you to tell me about this painting. If I were to hand this to the students in my class without an explanation, and I would just ask them to start asking questions, they would all come up with different ideas. And they might ask, why are we doing this? And it might be because we want to determine the authenticity. We might want to understand how it's degrading. We might want to understand how to preserve it, whether it's been preserved before, where it came from, who painted it, what was its cultural purpose, what is the location, do we want to repatriate it? In other words, was this painting stolen and do we want to give it back? Does it have any cultural value? But if I were in front of the audience right now and I could talk to you directly, I would get some interesting responses, I'm sure. I think you'll all agree, though, that this is probably a masterpiece. Those of you who are familiar with art, you probably would think that it was probably painted in the 1800s, maybe by some of the Hudson River artists. It's quite spectacular. I don't know how the artist created this incredible warm glow. It almost feels like the sun really is coming through the painting. Quite a remarkable piece of art. I'm actually making all that up because I actually painted this painting myself, and I know quite a bit about it. The reason I know a lot about it is because I actually painted this in 2012. And I went through a phase in my life where I made all my own paints. And so I made all the paint to paint this painting. I also made the canvas that it was painted on. It was painted on a piece of birch wood with some Belgian linen glued to it. I made my binder as well. And I painted it in 12 layers, roughly a couple of microns thick per layer. And so I understand the chemistry, and I understand the physics, and I understand the structure of this painting really well. It's incredibly complicated. A painting is an incredible structure. And to ask a student to analyze this is really quite challenging. So you can just imagine when I hand a painting to a student or a collection of students and I ask them to pull some information out of it, they start to think about what tools am I going to use? Can I go to the library and learn about this style, etc. So if I were to give this painting to a bunch of students in my class, I'd let them cut it up. I might be a little bummed out if they cut it up, but it's not worth a fortune. But if I ask you to analyze this painting, one of the most important paintings ever in history, The Last Supper by Leonardo da Vinci, if you were to go up and take an X-Acto knife and scrape a sample off of this, you might spend the rest of your life in jail. So analyzing a painting like this, which is what curators and museums are often challenged with, is a much more difficult and much more challenging thing to do. So I was fortunate enough to enter into a collaboration with the Walters Museum in Baltimore, Maryland, and they were analyzing some mummy portraits as part of what's called the Appear program. And in ancient Egypt, which was at the time called or is referred to as the Ptolemaic period, there was a contrast in artwork between what would be called Rome and traditional Egypt. And what ended up happening when the Romans occupied Egypt is that the Egyptians started to adopt some of the Romanesque or Greek-like art techniques. And this is a beautiful example of that. They painted portraits of themselves, but they painted these portraits in a Romanesque style. And then when they passed away, they would adhere these to their sarcophagus. And it's unclear why they did that. One theory is that by adhering these portraits that look very Romanesque to their sarcophagus, they reduced the death tax for their family. There was a tax when you died, just like there might be today, and they were able to minimize that tax and reduce the financial burden on their family. So these very interesting portraits, there's about 1,000 of them in the world, are kind of mysterious, and we're trying to understand them. And this is part of a program out of the Getty called the Appear program. This is a spectacular example of one of these portraits, and they vary in quality. And some of them look like they could have been painted by Rembrandt, and others look like they might have been part of a Fred Flintstone cartoon. There's a wide range of quality. This is the one that we analyzed, and the Walters Museum was kind enough to take a very tiny sample off of what's called a clavi on this fellow on the left. And the clavi, it's a little difficult to see in this particular image, but it was purple, which is a very interesting color. At this time in history, it would have been perhaps reserved for royalty. There were times in history where you could be put to death for wearing purple. And so this tiny little purple pigment was picked off with an X-Acto knife, basically, put into a container and shipped to me to analyze. And unfortunately, when I received it, we found that the particle was no longer there. So we spent the better part of 2 days searching for the particle in the box and eventually found it. And then we analyzed it. We discovered some really interesting things that we didn't expect. and knowing a bit about purple pigments, we were really surprised to observe aluminum and chrome in this pigment, which we don't normally see in purple pigments. We also found that there was a correlation between the aluminum and the potassium. And these two things painted a picture, no pun intended, for us that suggested that perhaps this was a synthetic purple pigment. Up until this point, we didn't know that the Egyptians had synthesized purple pigments. And so this was kind of a remarkable observation. So we set out to try to understand how the Egyptians might have synthesized the purple. So the first thing we did was to machine the pigment. This is an image of one of my students, Jennifer Burns, who's sitting at an instrument, an ion beam, similar to the SIMS that I described earlier. And Jatu goes in and machines out little areas of our particle and then pulls them out, and we can stick them in a TEM, or we can stick them in an atom probe, which operates very much like a SIMS, and analyze the chemistry and the structure. So to just kind of show you how remarkable this is, this couldn't have been done 30 years ago. This technology has been developed in recent years, the ability that is to machine samples this size. So this is a picture of the hair of one of my students, Jennifer Watkins, who's very good at taking your hair and tying it in knots and putting it in a microscope. If you ever tried this, it's not that easy. And then superimposed on this human hair is the particle. And it's at the exact same dimensions that, I'm showing this magnification of the hair. I also am showing one of the samples that we machined out of this particle, which is actually magnified by a factor of 10, so you can actually see it. And this is one of the little needles that we machined that we use for characterizing the chemistry. So we're able to get a ton of information out of a little tiny particle on a piece of art now. It's pretty remarkable. While it's destructive in a literal sense, it's actually non-destructive in a real sense, because the particles are so small that you actually can't see them. And so the damage is negligible. And this is a picture of one of my research faculty who's in my group, Yao Chao Wu, sitting at an instrument doing some chemical analysis. This is what's called a LEAP, or an atom probe. And he did the first chemical analyses ever done on using this technique on a mummy portrait, and was able to demonstrate that the particle itself is comprised of a number of things. It's an organic pigment comprised of hydrocarbons primarily. It also contains iron, lead, a little bit of chrome. It is a complex structure, it turns out, that contains precipitates. And you're down in the lower right, you're seeing some particles that are within the pigment. And these particles, it turns out, were identified as lead sulfide or lead carbonate, which came as a complete surprise to us. This is a chemical analysis of the particle in different regions. And this is some of the stuff that I kind of cut out of the presentation because it's a little bit boring. I apologize for all the detail here, but the point is we discovered that these particles contain significant amount of lead. They're rich in carbon and oxygen, suggesting that a significant portion is organic, which came as a complete surprise. There's a lot of aluminum and potassium, which are correlated, suggesting that there's alum in the pigment, which it indicates that it's synthetic. And then we also have chrome and iron. So to kind of make a long story short, which I have to do in this period of time, we determined that this was a synthetic pigment, and very likely was made with a plant or an insect. When we looked at the structure even further, we discovered that there's multiple zones in this, suggesting that there is some sort of a process of precipitation going on. And these white regions are regions rich in lead. They're either lead sulfide or lead carbonate. And our assessment drew us or brought us to a conclusion that the lead is probably associated with the container in which the pigment is made. And so here's a drawing from the British School of Archaeology back in 1908 showing an image of an Egyptian dyer's workshop. And they found these dyer's workshops had lots of lead crucibles, and they used to dye red. They used to dye all kinds of different colors, but red was very common. And so our theory is that the Egyptians discovered a way to make synthetic purple by taking red dye, adding either chrome and or iron to it, and shifting the color towards purple, which hadn't been demonstrated before, so we weren't sure that was true. The lead that was in the pigment very likely is just a byproduct of the synthesis process, and probably affects the color a little bit, but not a lot. So my students in my class set out to try to reverse engineer the way that the Egyptians made these pigments. And what they did is they gathered a whole bunch of plants and insects, ground them up, and made different red dyes, in some cases blue dyes. And then they added salts to them and shifted the color from, say, red into purple. And then to make it even more interesting, they took the dyes, added alum to it, and the dyes would adhere to these alum particles. You then dry it and you make a pigment. One of my students then took this product, this pigment, and mixed it in with beeswax, which was what the Egyptians would have done, and he painted a mummy portrait. And so we kind of went full circle. And this is a picture of the painting that the student created compared to our mummy on the left. And what made it even more fun is that this is actually a self-portrait, not unlike Da Vinci's, of the student who created this, Elagio Larino, who is pictured here doing some work at the Buffalo Bill Center in Cody. He then went on to work at the Yosemite, the museum in Yosemite. He then went on to the Walters Museum, and this year he is entering the PhD program at Delaware University in the Winterthur Museum, which is one of the best programs in the world. And he is a Renaissance man. He is an artist, a historian, a writer, a playwright, an actor, and a chemist. And so just kind of start to conclude, what we're trying to do is now correlate our discoveries associated with the pigment in the Walters Museum portrait with one in the Museum of Fine Art in Houston. And we just came out with a paper on this. It just got submitted this week, and it'll be hopefully published later this year in the International Journal of Ceramic Engineering and Science, if you're interested. And just to kind of tie things together, I'll say pun intended, I thought I would end with just a kind of a comment that, and this is a quote at the bottom of the picture from Brian Rosenberg, who's a retired president. This was in the New York Times recently. And he said, a society without grounding in ethics, self-reflection, empathy, and beauty is one that has lost its way. And so just to kind of tie all this together, I just want to say that, this is a time where, the arts, the humanities, the social sciences are more important than ever. We tend to really focus and emphasize the importance of science and engineering these days in advancing society. But I would argue that it's way more important right now to be focusing on the humanities and the arts. And so just want to put out a kind of a call to support those disciplines at the University of Utah and other universities. And I'll just end this brief presentation by saying thank you, and hope you come and visit us at the College of Mines and Earth Sciences. And by the way, this is a painting that the staff and the faculty and the students in our college have worked on over the last year or so. We have a event we call Painting with the Dean in our college a couple times a semester. And if you ever want to come and join us, feel free. So I'll stop there if there are any questions. And it's
Dean
always,
Butt,
it's
oh,
kind of interesting to stop with no applause, but I know you're all applauding in your living room. Thank you.
Dean Butt, thank you so much for that presentation. It was wonderful. If you have not done so already, please submit questions via the YouTube chat or send an email to the one provided in the chat, which is clubs@alumni.utah.edu. So this first question, how can the arts and sciences more effectively work together to solve challenges faced by the university, industry, and society?
Yeah, I mean, it's a good question. I mean, one of the issues with the arts and sciences, it is about silos on campus. It's also about funding. We all have separate funding sources, and finding ways to bring those funding sources together is difficult and it's rare. And so when I go after funding, I'm usually trying to get funding for energy applications or something like that. Funding sources for the arts and research in the arts and science of the arts is hard to come by. So we really need to change that somehow. And I do think one of the reasons I created this course actually is because it's a mechanism that allows me to collaborate with people on campus in arts through the classroom. And I can leverage, in a sense, the research that I do, and I can leverage the research that I can do. And so the course that I taught actually brought faculty from art and my college together to teach together. And so I do think we really need to think about developing what I'll call transdisciplinary curricula, where we bring these faculty together more often. And you got to force it. You got to make it happen. It's got to be deliberate. It's got to be intentional because it doesn't happen. The funding agencies don't do this. It doesn't happen through funding agencies. It has to be something that the university prioritizes and forces to happen. The one thing I'll say about bringing art and science together is if you're in science or engineering and you want to improve the diversity of your discipline, one of the best ways to do that is to connect with art, because art attracts an incredibly diverse group of people. And what I discovered is, it was just a great way to recruit diverse students. So there's lots of reasons to do it, but it has to be deliberate. It has to be intentional.
Thank you. Chuck Williamson asked, how do you deal with oxidation, of pigments separate from the original compositions?
Yeah, so good question. You must be reading papers because that's one of the big problems right now. And I actually have some slides on that, but I won't show you. I have a whole bunch of extra slides. So for example, the yellows are oxidizing all over the world right now in paintings. So the paintings of Munch and Van Gogh and Monet that were painted in the 1800s, maybe early 1900s, are degrading all over the world right now. And it happened kind of suddenly. And what they discovered was that, or what they've discovered is, and these are folks like Jennifer Mass, who was at the Winterthur Museum. She then went to the Van Gogh Museum, is now in New York. What they discovered is that the pigments that were used by some of these artists were substandard. So these yellow pigments are often made from cadmium, and it's a chemical process that they use to make them. And if the process of making the pigment is not complete, in other words, you might have some excess chlorine left over, things like that. In the end, the pigments are susceptible to oxidation. And unfortunately, the way that they prevent the oxidation is to seal the painting up and hide it and put it away. And what they've been doing with paintings, for example, Van Gogh's paintings, if you go to the Van Gogh Museum in the Netherlands, what you'll be looking at is actually not an original. And so they may have the original behind glass, shielded in dark glass, and you can't hardly see it, but next to it will be a replica. And so what museums are doing with these paintings that are oxidizing and degrading is putting them away and putting replicas out on display. And Fujifilm is one of the people that is involved in making these replicas. And you can purchase, if you want a Van Gogh, you can purchase a Van Gogh that is almost a perfect replica of the original, with the texture, with the cracks, with the fingerprints, everything. It's a pretty amazing technology. So that's one of the things they're doing. So you have to seal it up. You have to reduce the amount of oxygen. You have to have the humidity controlled at a very specific level. And because entropy happens.
What kind of things are you doing in the College of Mines and Earth Sciences to promote inclusion and diversity? And what impact have you seen from your efforts?
So we are trying to do many things. The College of Mines and Earth Sciences, as do many disciplines, have a long ways to go. Our college has been trying to improve its gender equity for quite a few years. The last few hires we've made, for example, have been female. We constantly try to improve our ethnic diversity. And one way to do that is by casting your net as wide as possible when you advertise for faculty positions, when you try to recruit students, et cetera. In the last year, we hired a diversity recruiter. We've hired someone in the college to help us revise our policies in order to assure that our tenure processes and the way we recruit faculty and students encourages diversity and supports diversity. You also have to develop a culture in the college that encourages diversity. And so some of the things that we've done in the college, for example, is to bring in organizations like Project Implicit from Harvard and the University of Virginia in order to train people in implicit bias. We have also implemented a what I'm calling a TLC Scholars Program or Fellows Program, where our faculty get trained in best practices in how to teach inclusively in the classroom, and we've held some workshops on that. We'll be bringing an organization from the University of Michigan in this year called Stride, which is focused on how do you develop an infrastructure for your program that encourages or facilitates hiring of diverse faculty. So there's lots of things we're doing. It's like safety. It never ends. It's something that you have to continuously do and practice every day. And we have a long ways to go. I'm confident we'll get there.
Are there any books, papers, articles, or anything like that that you would recommend looking up in order to learn more about the subjects you discussed today?
The book, one of my favorite books is the book Color by Victoria Finlay. It's a really amazing book. One of my favorite books on art and science is called Caveat Emptor. And it basically is a biography of, or autobiography of a forger. And he got away with forging paintings for many years, and it's a really fun story, actually. And then in terms of trying to kind of overcome bias and understand your own implicit bias, the book Blind Spot that I recommended earlier is a really good book to look at.
Thank you.
Yeah.
And I think you already touched on this a little bit, but how has a background in art helped you as a leader in science and education?
Yeah, that's a good question. I think my background in science and education has actually helped me to be an artist. I love art. I've loved art since I was a kid, and I kind of always wanted to be an artist. But I went into engineering because I wanted to actually eat and make a living. And I don't know if that was a mistake or not, but I've always enjoyed being an engineer too. So I think that in reality, my background in science and engineering have helped me to be an artist. In terms of my background in art, I think it's probably helped me to think a little bit more creatively when I'm trying to solve problems. It actually drives me to think about the world around me too. I'm always looking around trying to think about, why is the sky that color? Why, for example, does the color yellow disappear when things get farther away? Why are things out here in my periphery blurry when things here are focused? And so I do think, background in art does kind of make you always try to think about the world around you too. So yeah, good question.
Awesome, thank you. Well, Dean Butt, thank you for your incredible presentation and taking the time to join us tonight. If you want to learn more about the College of Mines and Earth Sciences, please visit cmes.utah.edu. And thank you to all that joined us this evening. We look forward to seeing you on Wednesday, July 8th from 7 to 8 p.m. Mountain Daylight Time, where Dr. Randall Olson, CEO of the John A. Moran Eye Center, and Dr. Gregory Hageman, John A. Moran Presidential Endowed Chair and Executive Director of the Sharon Eccles Steele Center for Translational Medicine, will speak about treatment for age-related macular degeneration, new hope in personalized medicine. We hope you have a wonderful evening. Thank you.
Thank you.